Hello and welcome everyone to week 5 problem solving session. I have posted the problem link in the chat box. So I hope you are able to access it. So today we'll be solving one problem related to graph, and so let us look at the problem. The problem statement is there in the chat box also, so you can open that or you can look at the screen. Okay, I hope you have read it, so I'll just read it and then we will discuss. I'll ask one of you to explain the problem. So the problem statement is that Tom has a maze which is a grid of h cross w squares with h horizontal rows and w vertical columns. The square at the ith row from the top and jth column from the left is an obstacle square if f if Sij is hash, and a free square if Sij is dot. From a free square you can move to a horizontal or vertical adjacent free square. Jerry cannot move out of the maze, move to an obstacle square, or move diagonally. And Tom will choose a origin square and a target square, which can be any free square, and give the maze to Jerry. Jerry will then travel from the origin square to the target square in the minimum number of moves required. Naturally, Tom wants to force Jerry to walk as much as possible. In this situation, find the maximum number of moves Jerry has to make, given that Tom can choose any origin and target square. So can any one of you just in 2-3 lines tell me what the problem statement is? Yeah, please go ahead.
Okay, so as I understand, the question asks us that we have two people, Tom and Jerry. Tom and Jerry. So uh, there is Tom somewhere on the grid, and there is Jerry who can start from anywhere on the grid according to our choice. And
Okay.
now they are basically moving through the maze from one point to the other, and they have to tell the maximum number of moves Jerry can make uh, while staying away from Tom and not being caught. Is it like that?
No. So the problem statement is, see the so there are two. So there is Tom and Jerry. Tom is going to tell Jerry origin and target, like the start and the end. And then Jerry needs to go from the origin square to the target square. I'll just take here the example. For example, we will be given a grid. Grid means a matrix of size h by w, where h is the number of rows, w is the number of columns. And a dot in that matrix represent that it is a free square, so you can move here. But if there is a hash, then you cannot move there. Okay, so here in the first input all are dot. That means that you can move to any square. So let's say if you are in the first square here, then you can move to horizontally to the second one, or you can move vertically to the below one. Okay, but you can move only horizontally or vertically, not diagonally. So from one you cannot move to this one. I hope that is clear. You cannot move diagonally, you can only move horizontally or vertically. Okay, now let's say you are Jerry. So I will, and I am Tom. So I will give you a start point. Like this could be the start point. One.
Excuse me, ma'am.
Yeah.
I think you have not shared your screen.
Oh, I am so sorry. Okay. I thought I had shared the screen. I'm sorry. Yeah. Okay. But did you guys look at the problem statement from that link that I had shared in the chat box?
Yes.
Okay, great. So I'll not read the problem again. Let us move directly to the sample input 1. So here you are given this matrix of 3 cross 3 size, and I was saying that if you are at this first index, like first square, 1 comma 1, then you can move horizontally to 1 comma 2 and vertically to 2 comma 1 here, which is highlighted, but you cannot move to 2 comma 2 because that is given in the problem statement. You can move either horizontally, vertically, but not diagonally. Okay, so that is the one case. Now in the problem statement says that Tom is giving Jerry a start point. Yeah, please go ahead.
Ma'am, could you please explain with the image drawing like that so that we can understand properly?
Sure. Is my whiteboard visible?
Yeah, visible, ma'am.
Yes.
Okay. Yeah, okay. So the first example is that so the input is a matrix, okay? And the matrix can have two values in each cell. One is hash, or for simplicity I am going to write cross, okay? One is cross and one is dot. Cross means obstacle, so you cannot move to an obstacle, and dot means free. It is free cell, you can move. So if you are at here first cell, you can move horizontally to this side, like second one, or you can move vertically downwards to this one, but you are not allowed to move diagonally. Okay, that's given in the problem statement. I'll just go here again. It's already open. Okay, here it is given from a free square you can move to horizontally or vertically adjacent free square. Okay, and you cannot move out of the maze, you cannot move to an obstacle square or move diagonally. So that is one thing. So it is just saying that if there were a cross here, then you cannot move here, this is not allowed. Okay, now next part of the problem statement says that if you are, then now you will be given a start point and a end point. Okay, so start could be given to you like that, this is your start point S and this is your end point. So Jerry will be given a start and an end, and it needs to move from start to end in the shortest possible, by the shortest path. Okay, so if you are given this is the start and this is the end, so then there are many ways possible, right? You can go here, then here, then here. Here I think every path is of length 4 only. Yeah, here every path is of length 4, but there could be many possible paths. So then so Tom is going to give the origin and the target, or we can say the start and end, it's same, like same thing. And Jerry will move from origin to target using the minimum number of steps. Coming back to the problem statement again. Any question? Okay. So that I've already told you there are two possible values in every square, hash and a dot. Okay, hash means obstacle, dot means free. From free square you can move to another free square, another adjacent free square, not anybody. You cannot take a jump to any other, but just the adjacent free square on the horizontal and vertical sides. You cannot move to an obstacle square, you cannot move out of the maze, and you cannot move diagonally. Now Tom will choose a origin square and a target square, which can be any free square, and give the maze to Jerry. Jerry will then travel from origin square to the target square in the minimum number of moves required. Now, naturally, Tom wants to make it difficult for Jerry by choosing origin and target such that Jerry needs to take the maximum number of steps. Okay? So, for example, coming back to the whiteboard again. So, if in the same example, let me just do it. We don't need this, so I'm just going to erase. And so Tom could have picked up end point as this only, this also, right? It can pick this. Then the number of steps Jerry would have required were 2. But here the optimal answer will come, like the optimal case is when Tom picks the target point as this one, the bottom rightmost, and the start point as the top leftmost. Did you understand? Any questions?
Explain once.
Okay. Sure. Those who have raised hands, if you have any particular question, you can ask. I'm explaining again.
Just for clarification,
Yeah.
is it like we have to choose the two farthest points in the maze that have their minimum distance as the maximum?
Yes.
Okay, thank you.
Yeah, we have to choose these 2 points in the maze such that the shortest distance between them is maximum. Yeah, that is right. Okay. So now to explain it again, let me take the another sample test case, which is here, this one. Okay, I'll try to copy this if I can. Yeah, so this is our next. So here you are Tom basically in this problem statement, and you have to choose the origin and target such that so as to maximize this length of the path between these 2 points, origin and target. Okay, now if you pick this one and this one, then what's the distance between them? Shortest distance between them. It is first. So it is. Sorry. Repeat.
Sorry. I mean 1.
Yeah, 1. Yeah, right. 1. So it's a undirected graph, right? If you can move from here to here, then you can move back also. Like, I'm just clarifying that. So it's an undirected graph, and every edge you can assume is of unit 1. weight 1. Okay, then the distance between these 2 points is only 1 unit. Now if you choose this to the tag, if you choose these 2 points as this, then the distance between them will be 2. If you choose it to some other value here, then the distance between them will be 1 2 3 4, right? 4. Now your, for this particular example, can you tell me which 2 points should be chosen such that the distance between them, shortest distance between them, is maximum?
Ma'am, it would be the lower left corner and the upper right corner. That will be also distance of 10.
Yeah. Abhilash, do you want to give the answer?
Yes, ma'am.
Yeah.
Madam, the first column and last row will be the origin, and first last column and first row will be the goal. Goal destination.
Sorry,
So that
can you repeat? So first, earlier you said first column and last row. I marked correctly, right? Red
yes,
circle.
ma'am. Yes,
Yeah.
ma'am.
And another one is,
Last column, first row.
okay. Yeah. Yeah. So you both told it correctly. So if we choose these 2 points, then the distance will be maximum, which is 10. Okay. So that is the problem. I hope you understood the problem. Now if you have any questions regarding the problem, then yeah.
Madam, can we say that to get the maximum, we have to visit every dots? I mean, every free space. Then
No. Uh, no, that won't. So you are saying, yeah. No, actually, this example is like this, but that's not true.
okay, okay, ma'am.
Yeah, so let's think about the problem. Uh, yes. Yeah. Any ideas?
Madam,
Yes.
sorry. It just guess, if we consider the I as a row and J as a column, then any I equal to I and any j equal to j will be considered the adjacent point, and we'll mark it as one unit then.
Sorry. I comma I, you are saying. Okay.
Uh,
Yeah, you mean you can move to the same. Okay, I'm just saying. Are you saying
can you?
that if you are at this,
Yeah, yeah.
if you are at,
For example,
yeah,
it just a guess. For example, if here first column there are three points are in the first column, then that means we can move to the first column properly, and we will got 2 points here.
yeah, you mean two distance.
Yeah.
Okay.
Then after that we'll consider second column,
Yeah.
but in second column only one point is uh, 1 point here in the row has same row as the adjacent one.
Yeah.
So we'll point it for plus one. That means two. We got two and plus one equal to three. Just like that, we'll continue and we'll got the maximum, something like that.
Okay, I think okay. Uh, but how will you do this traversal? Where will you start and how will you do?
Um,
Uh,
Yeah.
According to me, what I see is that we have to find the maximum shortest distance, right?
Right.
So we can let's say it would be a brute force approach only, but we can just make a record of all the distances between 2 points, any two uh, vertices that we have in this graph. This would be like a graph, right?
Yeah.
So we can have a dictionary or something like a note of the distances between every two nodes of the graph, and then we can just do a breadth first search to find that distances. And we can also try something like using the distances that we have to find the other distances as well. These two strategies I think can be useful for this.
Okay. Yeah, it makes sense, but okay. Mm. So then, just one question I want to ask. Why use BFS and not DFS?
In BFS, because we have to find the shortest distance, right? So
Yeah.
BFS would be efficient for finding that. We are going in a queue.
Hmm.
Uh, where once we find the shortest distance or the node target node that we are searching about, then we'll just break it. In DFS, if it goes in a very long path, let's say unluckily.
Okay.
So from here, let's say we are on the uh, first row and the third column, and from there we go to the left side, and then it will go completely to that side. And let's say we were finding the node at the fifth column and the first row, then it would be very long procedure for us. But for breadth first search, it would just be a bit better for shortest path, right?
Uh, so here I think DFS will not work. The reason I think is, I mean, pure like vanilla DFS will not work. If you make some changes to it, it may work. But so this is like, I mean, I will just. So let's assume that your input is something like this. And if your start is this and target is this, then what can DFS do is that you can go like this, right? And you will find that target is at 5 units away from start, but actually it is only 1 unit, right?
This one, this is also a case.
So that's why DFS will not work and BFS works, because BFS finds the shortest path, as you said. Now, what you are you suggesting something like that you will choose an origin and a target, and then you will find the shortest distance between them using BFS?
This one,
Yeah.
and then we make a note of all those.
Okay. So it is something, is it something like, so then how many origins are possible? Origins are h, sorry, so let me just for simplicity write that n is equal to h into w. Okay, so there we can just say there are n squares. So n squares can, any one of the n square can be origin, any one of the n squares can be target, right? So total n square pairs are there. And are you saying that we will run these n square pairs for every n every pair? We are going to run DFS and find the shortest distance between them, and then keep noting them and update whenever we find the find something more. We will keep updating the answer, right?
Yes, ma'am,
Yeah.
something like that.
Yeah, yeah. So that will work, but you, the same approach that you are saying, you can just improve it a little bit. I mean, you can improve it if you, I'll just give a hint, if you do not fix the target. You don't need to fix the target, that's what, so just think about it.
Yes, ma'am. That is also correct. We can just take a node and find the farthest node from it. That also using BFS and checking where the queue ends, right?
Yeah,
We can also do that. Yes,
I mean, you just start from a point of,
and
choose
we
a
can go to the
origin,
farthest where.
go to,
Yeah.
yeah, find the farthest, make a note of it, and then choose another origin, find the farthest, make a note of it, like apply BFS basically every time.
Yes, ma'am. Yes, sure about it.
Okay, okay. So a, so anyone wants to discuss any other approach? Did if you have any question related to the, like, did not understand the problem statement of anything? Yeah, yeah, please go ahead.
Madam, just
Yeah,
for example, we will means we will first find the original point, origin point, and then from that the approach I said earlier, like for
yeah,
this example, in the first row
yeah.
there are all points, all free spaces.
Hmm.
So first we will find the origin point.
Yeah.
For example, we will start from 0 0
Okay.
0 point, and we'll see to the to its right and to the down.
Yeah.
So here the right do not have any obstacle,
Yeah.
and the down also do not have any obstacle. So we will move to the down
Yeah.
and see and see again, do we have any obstacle to the right and down, and up until to the last node. We'll reach to the last node, that is 2.
Hmm. Yeah.
Yeah, and this node will be the our origin node. So we first got our origin node, and from the origin node we'll start this that approach, I just said, like we'll check um, again top one. We'll check, do we have obstacles to the top or right. If we do not have obstacle to the top, then we will move to the top, and that count as one. After that, we'll again compare something like
Okay.
that, ma'am.
Okay. Oh, so what you're explaining, I think, is very much like works for may work for this example, but you need to think it in a generic way, like how the traversal will happen. So uh, what you are saying is here is that I will move down two times and I will find the origin, but you do not know if it is the origin or not. It works for this example, but it does not work in that general way,
Mm.
right? So if you so here one thing that you suggested basically was that uh, you move to the right, you look on the right, you look down, then you go to the down one dot and you move further down. Now how did you make this, how, like, how did you come to the conclusion that this is the origin? That's not clear, like, right? You cannot
If
say that it
yeah,
is the origin.
I think what Abhilash is saying, it is something like a breadth of search only, that he's taking this, assuming this as the origin, and like checking down or right the farthest node that he can
yes,
approach, and then for the next approaching the farthest node again,
yes,
and
yes.
finding the farthest node.
Just
That's
like Ru- means what his name again? Yeah, just whatever he said is correct, ma'am.
Okay.
I just first assumed the 00 point as a origin, but then I check my left means adjacent every adjacent point, and then I change the origin. So that first we are going to discover where is the origin, and then after we'll start from that origin to the final destination. Something was like that.
Yeah, but I'm saying that uh okay, although it's not very clear to me, how will you conclude that it is the origin, like uh, basically uh, you need to, you, I mean, what you're saying, you need to think a little bit more about it. It's it currently I think it's not refined. Okay, another thing
yes,
is
I'm
if you are,
confused about origin finding as well. Can you explain it, Abhilash? Finding the origin first.
Sorry, ma'am.
I'm a bit confused about how will you find the origin first, and then you're saying that we'll find the origin first, and then we'll start from the farthest node.
Hello.
yeah, so our confusion is that you, how are you saying that when you have reached one point it is the origin? There needs to be one condition, that if you meet this condition then it is the origin. Let's say, like, is it the farthest node you can reach, or what is that, right? I mean, just can you,
Sorry, ma'am.
yeah, no problem.
Actually, yeah, my approach is actually wrong, ma'am. I just run a different example, and I got the wrong origin. So my origin was based on this diagram, and also the diagram just bit of change. So
Okay.
that was wrong. Yeah.
Yeah, it's okay, no problem. What I'm saying is just think a little bit more about the same direction that you are going to. It's not completely, don't just discard it, try to refine on it.
Okay, ma'am.
Yes, please go ahead. Yeah, Sudhakar, please go ahead. If you're not able to speak, you can write in the chat box.
Is my voice audible?
Yes, sir. Yeah.
Okay. Uh, are the source and destination given to us? I'm getting confused with this discussion.
No, they're not given. So the problem statement is that you will be not given a source and destination. You need to choose the source and destination in such a manner that the distance from source to destination is maximized.
Oh,
And also you need to take the optimal path from source to destination. It needs to be the shortest path from source to destination. Does
okay.
that make sense?
Yeah, you mean it consists of two problems, shortest path and
Yeah. Yeah. So given a source and destination, you need to find the shortest path between them.
okay, for that probably I'll try to place my solution.
Yeah, yeah, yeah.
Uh, I start from so I'll probably make a list of all the um, points. Can I call them as points?
Yes, yes.
Uh, for R equal to 1 to H, and then for C equal to 1 to W,
Yeah,
I will make a list of all the pairs,
sure.
and then I'll make the distance of source as 0,
Yeah,
and then I'll update the distance of its adjacent vertices
right.
as 1 and 1.
Yes.
Uh, and then I'll pick up the next shortest point. I'll search for the next point, which is the shortest, and then I'll update its adjacent vertices if their distance is not already recorded.
Yeah.
So this is how I go in a loop every time, finding out the next shortest point and then updating its adjacent vertices.
Right, right. Yeah.
So by the time I complete mm, the computation of the distance of all the points, I exhaust all the points, I should have the shortest distance between the source and destination.
Right. Yeah. You. That is correct to find the source. That is correct to find the shortest distance between a given source and destination.
And if a point is not reachable, then I'll drop that point. I'll not compute any shortest distance to that point if it is a hash point.
Yes. 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 That is correct. Yeah, basically you are starting from a source. You don't know, you are not fixing the destination, and you are finding the shortest path to every other point.
Yeah, I address the adjacent points first,
Yes.
and then I update their distances.
Yes.
Probably I initialize other than the source with probably some infinity value or the largest distance possible, or some maxint value.
Yeah. Yeah. So just so when you're saying yeah, yeah, that will work. And then you're saying that I will pick the next smallest, shortest,
Yes.
next node, which is
And
has
then
the shortest.
based on that, I'll update its adjacent vertices if they are reachable, if they are not hatches.
Yeah. So that is exactly what BFS will do. Breadth first traversal or breadth first search. That will work exactly like this. Like if we start from this node, we'll update that the distance here is 1, here is 1. Now what it does is that it maintains a queue. Okay, queue here. So initially the queue had 1 comma 1. I'm starting from index 1 here. Initially queue had 1 comma 1. Now we have removed 1 comma 1 and updated its adjacents, which are these. In the next step, we will update the queue as 2 comma 1 comma 1 comma 2. Now they have distance 1 comma 1. Every time, now you will take so I should probably be using here this only. Now you will take the front of the queue, pop the front of the queue, which is 2 comma 1, and visit its adjacents. So you will visit this node and you will then add this to the queue. So it will become 1 comma 2 comma 1 comma 3. Next again you will take the next, like front. So this queue data structure here is making sure that you visit the nodes in that shortest order only. Does that make sense? Like you added these two nodes before the node which had distance 2. So whenever you are taking out a node from the queue, it will be the it will be the node which has the shortest distance among all the unvisited node, all the nodes which need to be traversed, which have not been like whose adjacent have not been traversed yet. So I hope that this component of the problem is clear, that given one source and destination, you don't even need to fix the destination. You just choose a source and find the distances to all other points, and then you will find some point which is going to have the maximum distance from this point. Then for this source, that will be your destination. Right now you choose another source and again run BFS. Like in this example, okay. Like in this example, if we choose this as source, then this will become 1 1 2 2, right? Then you are going to try to visit this, let's say, but you cannot, there are no adjacent lefts which are not visited. Then you go here, visit its adjacent, this is obstacle, so you go here 3, then you will visit 3's adjacents, obstacle here, and upward already has been visited, so you go downwards, so this becomes 4. Then you visit 4's adjacent, it becomes 5, then 5 adjacent. Vertically there is obstacles, you move horizontally 6, then from here vertically 7, from vertically 8. So here, if this were the source, then this should be the destination, which is the farthest, right? But the another run of this could be when, if you choose, let me just copy quickly. Okay, so if this is here, if you choose this one as source S, then this will become 1, then you go here 2 3 4 5 6 7 8 9 10. I'm just doing very quickly, like this is how BFS will run. And then given this S, your destination will be at distance, will be this point D, and it will be at distance of 10 units. So is the solution clear?
One more thing I just saw in the solution is that we can optimize it further by just storing the longest path that we have. So let's say we are on the top left point in this example, and we have found that the longest path is, let's say, from uh, somewhere to the right and lower from there. Like the longest path from the top left corner would be 8, right?
Yeah.
And if we store the vertices that are in this path, then we shouldn't use these as an origin, because they have already checked the longest path for themselves.
uh, can you
Like let's
mm-hmm.
okay, let's say we are
Can
on
you
the top left
tell
corner.
for this
Okay,
one?
the top left, the starting node that we have as in the example that you have shown.
Yeah.
So let's say we are here.
Right.
So we traverse from here, and we find the longest path to be the one that goes from the right side, right?
Yeah.
So let's say we store this path, the
Right.
complete path that we have found for the longest one, and then with the nodes which are in this path already have their BFS called, right?
Mm-hmm.
For that we are like finding the longest path from them as well, right?
Right.
We move to a node and then we check if where the farthest we can go from there. So we don't have to call for BFS for them. We'll just need to call for the remaining nodes. Am I correct with that?
So you're saying that you don't need to, let's say, call BFS for three, like, sorry, this one, this
Yeah,
node
yeah.
particularly.
Not
Bec-
for three, not for two, not for one, not for four, five, six, seven, eight. But we'll need to call the BFS for the one and two on the lower side of S, because these are not among the shortest, longest path.
uh, okay, so
Something like,
you're saying that this cannot be a origin ever.
yeah, because we have a path from S to this, and this node already has the maximum length we can go check.
Hmm.
Yes, so it was something like that.
Mm,
But okay, I got it. Because in BFS we are not going backwards, so that will mean okay, I have made a mistake. Let's say we went to three, but we'll not go back to two and go to two
2 to
here.
1 to S to this
Yeah,
side.
yeah, we won't check the backward way.
Yeah.
Okay, I missed some. Sorry.
That's fine. There was any question? I think earlier there was a notification.
Madam,
Yes, yes.
madam, can you repeat the solution that was before discussed?
Sure, sure. You mean what we just discussed?
Yeah, the queue you just popped and pushed.
Oh, Q. Q. So Q, I was actually talking about graph algorithm, which is breadth first search. So breadth first search is the algorithm for graph traversal. So in this, what you do that you maintain a queue, okay, and the queue will contain the vertices that needs to be processed. I'm just reading from here because I find it a good description. So you create a queue which will contain the vertices to be processed, and you also can have a boolean array used which indicate for each vertex if it has been visited or not. Okay, so like for example here, if we do the breadth first search, let me just go. I'm so sorry. Yeah, so second. So if the circle one is the source here, so initially q has, you will put in your q s. Okay, so s is there in your q. I should use some other representation of the q here. Let's say q is there and this is your q. It has s currently. You know that q data structure whenever follows FIFO, first in first out. So whatever you add
Yes.
in the queue, right, okay, so initially there is s. So when you start the BFS traversal, you will pop the front of the queue, so that will be your s. So you just erase this. Now you are at source. Now from the source you will visit its adjacent, which are not obstacle or which have not been visited yet, right? So then you see that this, you can visit this node. So let us call this node S2. We will, so then you will push S2 in the queue, that this should be a node which you will visit the next time. Okay, and you will also, and you will mark it visited. Okay, then next time you will pop S2 from the queue, and when you pop S2 from the queue you will visit its adjacent, so it will be, let's say, S3 here, and you will add S3 to the queue. So actually I have started from S1, so you are not probably seeing when the queue will be actually useful. Let me just start from S here. If S1 was here, then you will visit these two. So Q will have S2 and S3, S2, S3. Okay, then next time you will pop S2, so your S3 will be here, there is no other entry here, so you will come here on S2, you will visit its horizontal and vertical, so S4 will be added here. Next time you are going to again take the front of the queue, which is S3 here, so your 4 will come here, you are going to visit S3, not S4. That was what I was saying. That's just a run of BFS. I'm just showing a run of the BFS.
Yes, ma'am. Yes, ma'am.
Okay.
I understand it.
Okay.
Yeah.
And in this manner, it makes sure that you get the shortest. You always traverse in this level, like level order. First you are here, you will go to its adjacent, and then for every adjacent you are going to make the next hop. DFS goes depth wise. Okay, and now let me quickly just walk you through this implementation part. So I will quickly go through it, and then you can, this will be available, you can go through it, and if you want you can just code and check it. So initially we have a adjacency matrix. In the adjacency matrix we have the same input actually, so one is hash, either hash or a dot. Then we create a distance matrix D. Okay, and there are two for loops. One is going from 0 to h, other from 0 to w. So I comma j is going to be our source. Okay, then we create this D matrix, which is a two-dimensional matrix, and every cell is currently marked having an integer value of -1. -1 indicates that it is not visited. Okay, I am using the same matrix to indicate visited and both, that what is the distance of this cell from the current origin, which is I comma j in this iteration of the for loops. Then we have a queue. Now in queue we are going to, since now source, since every cell is now represented with two values I comma j, so we take a pair of integers, pair int comma int, and we create a queue of where each element is a pair int comma int. We initialize that the answer when I comma j is the origin, then the answer is initially -1, and we will update it whenever we find anything more than this. Okay, if in the adjacency this is an obstacle cell, then we will not choose this as a source and we will continue. If it is not an obstacle, then we will push this in the queue and we will change its distance to 0, because it is the source, distance from itself is 0, and then we will do this is just BFS. We will continue this until the queue is empty. Every time we take the front of the queue, front of the queue is a pair of integer, so the first element is the row, second element is the column. Given a row and column, you can move in 4 directions, above it, below it, and left and right. So that's why there are these 4 if conditions. Okay, then every time what you are going to check, that this current like the adjacent cell is not out of the matrix, that you need to check. Okay, so for example, if you are looking at r minus 1 comma c, then r minus 1 should be greater than equal to 0, and it should be free cell. So there is this condition that it is dot, and then there is a condition that it is not visited, so that you can check if the distance is equal to -1. Then you are going to update its distance to this +1, what is the distance of the current cell. Then you are going to push it in the queue, and you are going to update the answer. Answer ij is equal to max of current answer ij and the distance of this adjacent cell. This you are going to do for the 4 adjacent cells. and in the end when the BFS terminates for the current I comma j, you are going to update your global answer. Take the maximum of the current answer with the answer ij. So that's like a simple implementation of this approach. Any question here? Like if you have any quick question, otherwise go
No,
back and
ma'am. We
see.
can continue, I guess.
Yeah. Okay. So another approach uh, is, I mean, I have actually not thought it through completely, but I think it will work. So that I'm going to share with you, and I would want you guys to also think about it. And if you have any ideas about it, then do let me know. So what we can do is that start from any node S. Choose any node, okay? It could be your first 0, 0. Start from there and do BFS. And then find some farthest. You will find some nodes. You will find the distance to every free cell. Now choose the free cell which is the farthest from it, and then do breadth first search from that farthest node to find the other farthest node, and and these two will be the origin and target. I mean, that's how I think that will also work.
Then yes, I think you're right there, because if we reach from one node to the farthest of it and we run a breadth first search from there,
Yeah.
then we can reach to the node that those nodes that are missed, right? Is it something like that?
Could you repeat?
Ma'am, I mean that let's say we are starting our breadth first search from some arbitrary node
Yeah.
that is a dot, and then we go to the farthest point
Yeah.
from it,
Yeah.
right?
Right.
We are moving in one path
Yeah.
and we reach to the farthest node,
Yeah.
and then when we run the breadth first search from that
Yeah.
point to the next point, then it will give us either the path back or the another path that is longer than that. It won't give us a shorter path, right? So
Yeah, I mean, it won't give the shorter path.
yes,
So it is.
yeah,
Let's
yeah, yeah.
try
I
to see.
think this will work. Yeah.
Yeah, so since here it's like a tree only. When we are
Yes.
doing this breadth first search, it's like a tree. So it is like, if I start from here, if this is S, I'm sorry, I need to. If this is S, then I might go to some E1 here, might go to some E2 here, E3 here, and this path could be at a distance of, let's say, 10, this 7, this is 6. Now if I choose E1, now I'm saying that first do a breadth first from S. You will find these different directions. You will find some end points which are farthest from S. Okay, now in among those, choose the one which is farthest from S, which is E1. From E1, do the breadth first search again. So basically then you will come back like this or this. So when you E1 to E2 will be 17 and E1 to E3 will be 16. So in 2 BFS, first BFS find the farthest, and from the farthest then again run one more BFS and find and whichever is your farthest node, that will be the other endpoint.
Yes, ma'am, got it.
Okay, so yeah, I think that makes sense to me. I am quite convinced that it works, and so to think about
Ma'am,
it.
just one question.
Yeah.
I'm just thinking, like, is will this be guaranteed to be completed in two steps, right? Two breadth first searches. First would find us the origin, second would find us the target, like that.
Yeah. Yeah. Like that.
Yes. Okay, ma'am.
Yeah. Okay. Okay, so that's all I had for today. So do try to implement this, and if you have any questions, then do let me know. Okay. Shall we end the session, or do you have any questions?
Hello, ma'am.
Yeah.
It just does this meeting means every meeting has recorded or anything?
Yeah. Yeah. Every